The hydronium cation, also known as hydroxonium, is the positively charged polyatomic ion with the chemical formula H3O+. Hydronium, a type of oxonium ion, is formed by the protonation of water, H2O. This cation is often used to represent the nature of the proton in aqueous solution, where the proton is highly solvated. The reality is far more complicated, as a proton is bound to several molecules of water, such that other descriptions such as H5O2+, H7O3+, and H9O4+ are increasingly accurate descriptions of the environment of a proton in water. The ion H3O+ has been detected in the gas phase. Determination of pH. It is the presence of hydronium ions relative to hydroxide that determines a solution's pH. Water molecules auto-dissociate into hydronium and hydroxide ions in the following equilibrium: 2H, 2OO plus H, 3O+. In pure water, there is an equal number of hydroxide and hydronium ions. At 25 degrees Celsius and atmospheric pressure, their concentrations are approximately equal to 1.0 A, 10^7 mol unregistered trademarked Ma3. For these conditions, H3O+ equals A10 a pH, so P high equals A7 is defined as neutral. A pH value less than 7 indicates an acidic solution, and a pH value more than 7 indicates a basic solution. Nomenclature. According to IUPAC nomenclature of organic chemistry, the hydronium ion should be referred to as oxonium. Hydroxonium may also be used unambiguously to identify it. A draft IUPAC proposal also recommends the use of oxonium and oxidanium in organic and inorganic chemistry contexts, respectively. An oxonium ion is any ion with a trivalent oxygen cation. For example, a protonated hydroxyl group is an oxonium ion, but not a hydronium. Structure. Since O+ and N have the same number of electrons, H3O+ is isoelectronic with ammonia. As shown in the images above, H3O+ has a trigonal pyramid geometry with the oxygen atom at its apex. The HOH bond angle is 113.6 a degree, and the center of mass is very close to the oxygen atom. Because the base of the pyramid is made up of 3 identical hydrogen atoms, the H3O+ molecule's symmetric top configuration is such that it belongs to the C3V point group. Because of this symmetry and the fact that it has a dipole moment, the rotational selection rules are Ij equals AA plus or minus 1 and Ik equals A0. The transition dipole lies along the C-axis and, because the negative charge is localized near the oxygen atom, the dipole moment points to the apex, perpendicular to the base plane. Clusters including more than one water molecule have been detected. At high pressures, liquid phase clusters can include up to 6 water molecules. Acids and acidity. Hydronium is the cation that forms from water in the presence of hydrogen ions. These hydrons do not exist in a free state, they are extremely reactive and are solvated by water. In general, an acidic solute is the source of these hydrons. However, hydroniums exist even in pure water. This special case of water reacting with water to produce hydronium ions is commonly known as the self-ionization of water. The resulting hydronium ions are few and short-lived. pH is a measure of the relative activity of hydronium and hydroxide ions in aqueous solutions. In acidic solutions, hydronium is the more active, its excess proton being readily available for reaction with basic species. Hydronium is very acidic. At 25 degrees Celsius, its pKa is a 1.74. It is also the most acidic species that can exist in water. Sea-leveling effect. Any stronger acid will ionize and protonate a water molecule to form hydronium. The acidity of hydronium is the implicit standard used to judge the strength of an acid in water. Strong acids must be better proton donors than hydronium, otherwise a significant portion of acid will exist in a non-ionized state. Unlike hydronium in neutral solutions that result from water's autodissociation, hydronium ions in acidic solutions are long-lasting and concentrated, in proportion to the strength of the dissolved acid. pH was originally conceived to be a measure of the hydrogen ion concentration of aqueous solution. We now know that virtually all such free protons quickly react with water to form hydronium. Acidity of an aqueous solution is therefore more accurately characterized by its hydronium concentration. In organic syntheses, such as acid-catalyzed reactions, the hydronium ion, H3O+, can be used interchangeably with the H+ ion. Choosing one over the other has no significant effect on the mechanism of reaction. Solvation: researchers have yet to fully characterize the solvation of hydronium ion in water, in part because many different meanings of solvation exist. A freezing point depression study determined that the mean hydration ion in cold water is approximately H3O+, H2O, 6. On average, each hydronium ion is solvated by 6 water molecules, which are unable to solvate other solute molecules. Some hydration structures are quite large. The H3O+, H2O, 20 magic ion number structure might place the hydronium inside a dodecahedral cage. However, more recent ab initio method molecular dynamics simulations have shown that, on average, the hydrated proton resides on the surface of the H3O+, H2O, 20 cluster. Further, several disparate features of these simulations agree with their experimental counterparts, suggesting an alternative interpretation of the experimental results. Two other well-known structures are the Sogndal cations and Eigen cations. The Eigen solvation structure has the hydronium ion at the center of an H9O+, 4 complex in which the hydronium is strongly hydrogen bonded to 3 neighboring water molecules. In the Sogndal H5O+, 2 complex, the proton is shared equally by 2 water molecules in a symmetric hydrogen bond. Recent work indicates that both of these complexes represent ideal structures in a more general hydrogen bond network defect. Isolation of the hydronium ion monomer in liquid phase was achieved in a non-aqueous, low nucleophilicity superacid solution, HFSBF, 5SO2. The ion was characterized by high-resolution O17 nuclear magnetic resonance. A 2007 calculation of the enthalpies and free energies of the various hydrogen bonds around the hydronium cation in liquid protonated water at room temperature and a study of the proton hopping mechanism using molecular dynamics showed that the hydrogen bonds around the hydronium ion are quite strong compared to those of bulk water. A new model was proposed by Stoyanov based on infrared spectroscopy in which the proton exists as an H13O+, 6 ion. The positive charge is thus delocalized over 6 water molecules. Higher solvation deuteronium ions have been detected by mass spectrometry. Solid hydronium salts: for many strong acids, it is possible to form crystals of their hydronium salt that are relatively stable. Sometimes these salts are called acid monohydrates. As a rule, any acid with an ionization constant of 109 or higher may do this. In general, acids whose ionization constant is below 109 cannot form stable H3O+ salts. For example, hydrochloric acid has an ionization constant of 107, and mixtures with water at all proportions are liquid at room temperature. However, perchloric acid has an ionization constant of 1010, and, if liquid anhydrous perchloric acid and water are combined in a 1:1 molar ratio, solid hydronium perchlorate forms. The hydronium ion also forms stable compounds with the carborane superacid HCB, 11 hours, CH3, 5B, 6. X-ray crystallography shows a C3V symmetry for the hydronium ion, with each proton interacting with a boron atom each from 3 carborane anions 320 pm apart on average. The H3O, HCB, 11HCl, 11 salt is also soluble in benzene. In crystals grown from a benzene solution, the solvent co-crystallizes and H3O, benzene, 3-cation is completely separated from the anion. In the cation, 3 benzene molecules surround hydronium, forming pi-cation interactions with the hydrogen atoms. The closest approach of the anion at chlorine to the cation at oxygen is 348 pm. There are also many examples of hydrated hydronium ions known, such as the H50+, 2 ion in HCl 2 hours, 2O, the H70+, 3 and H90+, 4 ions both found in HBr 4 hours, 2O, atmospheric H30+, the hydronium ion has been found in higher atmospheric layers. Interstellar H30+, motivation for study. Hydronium is an abundant molecular ion in the interstellar medium and is found in diffuse and dense molecular clouds as well as the plasma tails of comets. Interstellar sources of hydronium observations include the regions of Sagittarius B2, Orion OMC1, Orion BNA Eurowork 2, Orion KL, and the comet Hale-Bopp. Interstellar hydronium is formed by a chain of reactions started by the ionization of H2 into H+, 2 by cosmic radiation. H30+ can produce either OA or H2O through dissociative recombination reactions, which occur very quickly even at the low temperatures of dense clouds. This leads to hydronium playing a very important role in interstellar ion-neutral chemistry. Astronomers are especially interested in determining the abundance of water in various interstellar climates due to its key role in the cooling of dense molecular gases through radiative processes. However, H2O does not have many favorable transitions for ground-based observations. Although observations of HDO could potentially be used for estimating H2O abundances, the ratio of HDO to H2O is not known very accurately. Hydronium, on the other hand, has several transitions that make it a superior candidate for detection and identification in a variety of situations. This information has been used in conjunction with laboratory measurements of the branching ratios of the various H30+ dissociative recombination reactions to provide what are believed to be relatively accurate OA and H2O abundances without requiring direct observation of these species. Interstellar chemistry, H30+ is found in both diffuse and dense molecular clouds. By applying the reaction rate constants corresponding to all of the currently available characterized reactions involving H30+, it is possible to calculate K, T, for each of these reactions. By multiplying these K, T, by the relative abundances of the products, the relative rates for each reaction at a given temperature can be determined. These relative rates can be made in absolute rates by multiplying them by the H2. By assuming T equals 10 K for a dense cloud and T equals 50 K for a diffuse cloud, the results indicate that most dominant formation and destruction mechanisms were the same for both cases. It should be mentioned that the relative abundances used in these calculations correspond to TMC1, a dense molecular cloud, and that the calculated relative rates are, therefore, expected to be more accurate at T equals 10 K. The three fastest formation and destruction mechanisms are listed in the table below, along with their relative rates. Note that the rates of these 6 reactions are such that they make up approximately 99% of H30+'s chemical interactions under these conditions. More about these reactions were observed and recorded regarding Hale-Bopp data. Finally, it should also be noted that all 3 destruction mechanisms in the table below are classified as dissociative recombination reactions. It is also worth noting that the relative rates for the formation reactions in the table above are the same for a given reaction at both temperatures. This is due to the reaction rate constants for these reactions having I² and I³ constants of 0, resulting in K equals I plus or minus $alpha, which is independent of temperature. Since all 3 of these reactions produce either H2O or OH, these results reinforce the strong connection between their relative abundances and that of H30+. The rates of these 6 reactions are such that they make up approximately 99% of H30+'s chemical interactions under these conditions. Astronomical detections, as early as 1973 and before the first interstellar detection, chemical models of the interstellar medium predicted that hydronium was an abundant molecular ion and that it played an important role in ion-neutral chemistry. However, before an astronomical search could be underway, there was still the matter of determining hydronium's spectroscopic features in the gas phase, which at this point were unknown. The first studies of these characteristics came in 1977, which was followed by other, higher-resolution spectroscopy experiments. Once several lines had been identified in the laboratory, the first interstellar detection of H30+ was made by two groups almost simultaneously in 1986. The first, published in June 1986, reported observation of the JKVT equals 11 Euro 21 plus transition at 307,192.41 MHz in OMC1 and SGRB2. The second, published in August, reported observation of the same transition toward the Orion KL nebula. These first detections have been followed by observations of a number of additional H30+ transitions. The first observations of each subsequent transition detection are given below in chronological order. In 1991, the 32+ Euro 22 transition at 364,797.427 MHz was observed in OMC1 and SGRB2. 1 year later, the 30+ Euro 20 transition at 396,272.412 MHz was observed in several regions, the clearest of which was the W3IRS5 cloud. The first far IR43 Euro 33+ transition at 69.524 micrometer was made in 1996 near Orion BN Urk-2. In 2001, 3 additional transitions of H30+ were observed in the far infrared in SGRB2. 21 Euro 11+ transition at 100.577 micrometer, 11 Euro 11+ at 181.054 micrometer and 20 Euro 10+ at 100.869 micrometer. See also, hydron, hydride, hydrogen anion, proton affinity, standard hydrogen electrode, ocean acidification, references. External links, ChemSpider equals 109935, Journal of Chemical Physics.